Millions of us survived high school algebra by reciting catchy songs or memorizing bizarre stories about negative B's going to radical parties. We did all that to memorize the solution to this specific problem, the standard quadratic equation, where a, b, and c are known numbers, and we need to find x. For most students, trying to solve this is their very first encounter with mathematics as an exercise in pure rote memorization. We hand teenagers a complex string of symbols and tell them to plug in the numbers. This creates an educational environment where passing a memory test takes priority over actual logic. The traditional curriculum typically offers 3 paths to find the answer. The first is factoring, which often devolves into an inefficient, frustrating game of guess and check to find 2 numbers that fit the equation perfectly. Then there is completing the square. This method requires 5 distinct, exhaustive algebraic steps, forcing the student to balance fractions and negative signs across multiple lines of work. And finally, the infamous quadratic formula. It is a dense cluster of variables, where a single missed negative sign, or a tiny arithmetic error under the square root, what mathematicians call the discriminant, dooms the entire calculation. These methods demand mechanical perfection instead of logical intuition. By relying on clunky, error-prone processes, we completely miss a much simpler path. In 2019, Carnegie Mellon math professor Po-Shen Lo realized we can bypass the formula entirely, relying instead on a universal piece of logic. First, we set the squared term to 1. In this simplified form, the 2 answers, or roots, we are looking for must adhere to an absolute mathematical rule. They always add up to the opposite of the middle number, negative b, and multiply to equal the final number, c. Here is the logical leap. If 2 unknown numbers add up to negative b, their exact average has to be exactly half of that, negative b divided by 2. Because they share this exact average, we can define the 2 roots strictly by their distance from that center point. One root is the average plus a common unknown offset, which we will call z. The other is the average minus that exact same offset. The frustrating guess and check process is gone. The entire problem is now reduced to finding one single unknown distance, z. To find that distance, we look at the second absolute rule. Our 2 roots must multiply together to equal the final number, c. We set up the multiplication. The average plus z multiplied by the average minus c equals c. Because these terms are identical except for the plus and minus, they form what algebra calls a difference of squares. When you multiply them, the messy male terms cancel out perfectly. The equation collapses into something remarkably simple. The average squared minus z squared equals c. Let's test it on an actual equation, like x squared minus 2x plus 4 equals 0. The average is 1, and the product is 4. So 1 squared minus z squared equals 4. That means z squared is negative 3. The offset is the square root of negative 3, and we instantly have our 2 roots. No dense formula required. By reverse engineering the mechanics of how roots work, we replace a chaotic formula with a clean, bulletproof algorithm. It works instantly, every single time. The deepest irony here is that the foundation of this shortcut, knowing that the roots add and multiply to specific coefficients, was actually known to the ancient Babylonians over 4 millennia ago. But early mathematicians lacked a complete understanding of complex imaginary numbers. When equations didn't yield clean, real answers, they couldn't use this trick, so they leaned on the clunkier visual geometry of completing the square. That historical compromise calcified. It was written into textbooks, institutionalized in classrooms, and passed down unquestioned through generations of teachers. Educational inertia kept a vastly simpler solution hiding in plain sight for 40 centuries. Stepping away from the quadratic formula changes the way we value mathematical skill. It moves the focus from perfect recall to the ability to reason through a problem from scratch. This method treats math as a flexible toolkit. Instead of following a rigid procedure, you're applying the underlying rules of numbers to solve the puzzle. When we prioritize logic over memorization, even a deeply entrenched 4,000-year-old problem collapses into a remarkably simple solution.